For years, the SR-71 was America's untouchable spy plane, faster than any missile, higher than any jet. Then, it was gone. No warning, no replacement. But buried inside Lockheed's Skunk Works, engineers built something even darker, faster, and deadlier. It's not a rumor anymore, it's the SR-72. The original Blackbird represented a technological leap that defined Cold War aviation. Lockheed equipped the SR-71 with two Pratt & Whitney J58 turbojet engines capable of reaching Mach 3.2 at altitudes exceeding 85,000 feet. Pilots wore pressure suits identical to those used by astronauts because the cockpit environment at operational altitude matched conditions found in low Earth orbit. The aircraft's design incorporated approximately 85% titanium alloy in its structure, with polymer composites filling the remainder. Engineers at Lockheed's Skunk Works facility selected a specific titanium alloy that remained workable during manufacturing but could withstand the extreme thermal stress generated during sustained Mach 3 flight. The SR-71 skin featured corrugated panels rather than smooth surfaces. This design choice allowed the airframe to expand and contract with temperature fluctuations of several hundred degrees without structural failure. On the ground, fuel leaked from the aircraft's tanks through gaps in the fuselage panels. These gaps closed only after the airframe heated during flight, causing thermal expansion that sealed the structure. The outer windshield consisted of 3 layers of quartz glass with active cooling channels between each layer. The navigation window used solid quartz ultrasonically welded to a titanium frame, withstanding surface temperatures reaching 600 degrees Fahrenheit during operational missions. Lockheed applied a specialized black ferrite iron paint across the entire airframe. This coating absorbed radar energy and radiated heat more efficiently than bare metal, reducing both radar cross-section and thermal stress. The Air Force added cesium-based compounds to the JP-7 fuel specifically to reduce the radar signature of the engine exhaust plumes. Between 1964 and 1998, the SR-71 faced more than 4,000 surface-to-air missiles during reconnaissance missions. None achieved a successful intercept. The U.S. Air Force retired the SR-71 fleet in 1998, with NASA operating the final 2 airworthy examples until 1999. Congress cited operational costs as the primary factor in the decision. Each flight hour required extensive maintenance, specialized fuel handling, and dedicated ground crew training. The end of the Cold War reduced the perceived need for high-altitude reconnaissance aircraft as satellite technology advanced and unmanned aerial vehicles entered service. In the early 2000s, Lockheed Martin's Skunk Works division initiated preliminary studies for a hypersonic reconnaissance platform. Between 2006 and 2007, Lockheed engineers partnered with Aerojet Rocketdyne to develop an engine capable of sustained hypersonic flight. Aerojet applied scramjet technology supersonic combustion ramjet to create a propulsion system that could operate efficiently across an unprecedented speed range. Traditional turbojet engines perform optimally from 0 to Mach 2.5 but lose efficiency at higher speeds due to compressor limitations and thermal stress. Ramjet engines function efficiently between Mach 3 and Mach 6 but cannot operate below Mach 0.5 because they require supersonic airflow to initiate combustion. The solution emerged as a turbine-based combined cycle system. This design integrates a conventional turbojet engine with a scramjet engine sharing common inlet and exhaust structures but maintaining separate airflow paths. The turbojet provides thrust during takeoff, acceleration through transonic speeds, and landing operations. At approximately Mach 3, the system transitions to scramjet operation for hypersonic flight segments. Lockheed considered 2 specific turbojet engines as candidates for the turbine component: the Pratt & Whitney F100 and the General Electric F110. Both engines power operational U.S. fighter aircraft, including the F-15 Eagle and F-16 Fighting Falcon. Material science presented significant challenges for the SR-72 program. Aircraft traveling at Mach 6 generate surface temperatures exceeding 3,500 degrees Fahrenheit through aerodynamic heating. Standard aerospace aluminum alloys melt at approximately 1,200 degrees Fahrenheit. Steel maintains structural integrity until reaching approximately 2,500 degrees Fahrenheit. The SR-72 airframe requires composite materials incorporating high-performance carbon fiber, ceramic matrices, and metal alloys originally developed for intercontinental ballistic missile re-entry vehicles and space shuttle thermal protection systems. On November 1, 2013, Lockheed Martin publicly confirmed SR-72 development through an official announcement on the company website. The statement specified the aircraft would achieve speeds up to Mach 6, exactly double the SR-71's maximum velocity. Lockheed emphasized the technological gap between the two programs, noting the SR-71 was designed using slide rules and paper drafting techniques, while the SR-72 incorporates advanced computational fluid dynamics, digital manufacturing, and millions of lines of software code. The announcement referenced experience gained from the Falcon Hypersonic Technology Vehicle 2 program. This experimental rocket-launched vehicle completed test flights specifically to collect data on hypersonic aerodynamics, thermal management, guidance systems, and control surfaces at speeds exceeding Mach 20. The program generated critical information about shockwave interactions, boundary layer behavior, and materials performance under extreme thermal loads. In 2016, Lockheed Martin CEO Marillyn Hewson stated the company approached a technological breakthrough enabling construction of a hypersonic demonstrator comparable in size to the F-22 Raptor for less than $1 billion. 2 years later, Lockheed Martin Vice President Jack O'Banion confirmed advances in additive manufacturing and computational modeling eliminated previous barriers to hypersonic aircraft development. O'Banion specifically stated, "We couldn't have made the engine itself. It would have melted down into slag if we tried to produce it 5 years ago. But now we can digitally print that engine with an incredibly sophisticated cooling system integrated into the material of the engine itself." The SR-72 will likely carry hypersonic missiles as its primary armament. During the 1960s, Lockheed demonstrated successful air-to-air missile launches at speeds exceeding Mach 3 using YF-12 interceptor prototypes. These tests proved the concept of weapon release in high-speed, high-temperature flight environments. Modern hypersonic missiles under development by U.S. defense contractors will integrate directly into the SR-72's mission profile. In 2022, Lockheed Martin's Skunk Works division collaborated with Paramount Pictures on the film Top Gun: Maverick. The movie featured a fictional hypersonic aircraft designated Darkstar. Lockheed provided technical consultation for the aircraft's design, propulsion system, animation, and operational sequences. Approximately 1 month before the film's theatrical release, a Lockheed Martin communications director posted on social media that the Darkstar trailer provided a sneaky peek at potential SR-72 characteristics. Producer Jerry Bruckheimer later stated Chinese intelligence services redirected a reconnaissance satellite to photograph the full-scale Darkstar prop at the filming location, apparently believing it represented an operational U.S. military prototype. Initial program timelines projected single-engine SR-72 demonstrator flights beginning in 2025. Current assessments suggest 2027 to 2029 represents a more realistic timeframe for flight testing. The U.S. Air Force's long-term hypersonic development roadmap explicitly includes the SR-72 program, confirming dedicated budget allocation and continued development funding. The aircraft aligns with broader Pentagon efforts to maintain technological superiority over Russian and Chinese hypersonic weapons programs. Program costs remain classified. However, the SR-72 will certainly require greater investment per airframe than any fighter aircraft currently in development. The Next Generation Air Dominance Program, the U.S. Air Force's sixth-generation fighter initiative, involves multiple aircraft types in larger production quantities. The SR-72 will operate in far smaller numbers with significantly more complex manufacturing requirements. Export versions appear unlikely given the classified propulsion technology, thermal management systems, and hypersonic flight control software integrated into the design. The SR-72 represents a fundamental shift in reconnaissance aircraft philosophy. The basic variant will operate autonomously without onboard crew. A piloted variant exists as an optional configuration, This architecture distributes sensing, targeting, and strike capabilities across multiple platforms operating in coordinated formations. Lockheed Martin has not released updated SR-72 timelines or confirmed operational dates. The program continues under classification levels that restrict public disclosure of technical specifications, test results, and production schedules. Aviation observers note increased activity at Air Force Plant 42 Inches, Palmdale, California, where Skunk Works maintains its primary development facilities. However, the site also hosts Boeing, Northrop Grumman, and other defense contractors conducting classified programs simultaneously. The SR-72 will not replicate the SR-71's distinctive appearance. Hypersonic aerodynamics require different geometric solutions than those employed in 1960s Mach 3 designs. Whatever emerges from Skunk Works will reflect 5 decades of computational design, advanced materials, science, and operational lessons learned from stealth programs, unmanned systems, and hypersonic test vehicles.